Good morning, this is Deep Generative Model. Start from this week, we are going to talk about diffusion models. Currently, diffusion model is the most popular way to generate images. I believe that many of you have already tried it before, but for the sake of completeness, I'm going to show some usage of the diffusion models so that just in case if you haven't heard it before, you can have an idea of what it is. So one way to use that is to use some online AI services. A lot of AI services specifically for generating images like runway ML. But since the diffusion model is so popular, most of the general AI chat platform like ChatGPT or Bard or Microsoft Copilot, all of them provide the ability to generate image and they are using diffusion models. So for this example, this one is using Microsoft Copilot. The prompt I'm using is create an image of a rabbit knight standing in front of a castle, 3D rendering in Unreal Engine high quality. So you can see that the generated image is something like this one. And you can download it. And you can do that in ChatGPT and for Gemini, previously known as Bard. This is the image generated by Gemini. If you don't want to use online service, you want to create the image by yourself, you can still run the model locally. One way to do that is use the A1111 web UI. And the other popular way is using Comfy UI. So this one is an example of using Comfy UI, and I'm using the simple default workflow and using the classic Stable Diffusion 1.5 model to generate the image. You can see the work on the fly. So it is working and generating, and this is a generated image. And I can do it again to generate different images. There is a huge ecosystem built around diffusion model, like text to image, image to image, and ControlNet, and video generation, and 3D model generation. We're going to cover it later, but right now we're going to talk about how the diffusion model works and some theories behind it. There are two major approaches to introduce the theory and the principles behind the denoise diffusion models. One is using the denoising approach, and the other is using the score-based model and score matching. In our lecture, we have a very concise description of what the score-based model and the score matching is. Followed by that is a short list of milestone papers that introduce the denoise diffusion model. The first paper is this one. This one introduces the basic mathematics behind the denoise diffusion models. So we have two processes. One is the forward pass, and the other is a backward pass. Given an image, we add in the noise into the image. So you can see that at step 0, we have clear images, and progressively adding a noise into the image. By adding some noise onto the image, we got X1, and by introducing even more noise into the images, we got S2, and so on. We have X3, X4, and to XT. The backward pass is the denoising pass. So start from the very noisy image. We denoise image step by step. So that's a basic idea of the denoise diffusion models. We first add noise into the images by a fixed schema. Then we use the deep learning to learn how to denoise the images. So basically, the models we trained for the diffusion model is a denoise model. So here you can see the mathematical formulas. So this is a very big picture of how the diffusion model works. We're going to detail a little bit later. Later on, there are many papers follow this approach and improve the method and can already generate some images with very high fidelity, like this one, Denoise Diffusion Probability Models, which stands for DDPM. It already can generate very realistic face images, and it has already been considered as the most promising and maybe the best log likelihood-based model. However, the image quality is still a little bit behind the best game models back then. So finally, a paper that called the Diffusion Model Bit Get. It introduced more modern architectures to implement the diffusion models because previous models are more research and academic oriented. So this one tried to use the modern architectures like transformers to implement the diffusion model to see how good it can achieve. It turns out it can actually beat the best game models back then. And you can see the quality of the image generated using the models in this paper. After this paper published, people started to notice the power of diffusion models. Therefore, a large amount of research was initiated following the publication of Stable Diffusion. Even those outside the academic circle began to recognize and use diffusion models. As a result, there was an even greater surge of research. The application of diffusion model extended beyond image generation to areas like video generation, 3D object generation, and even audio generation. Let's go back to the theoretical foundation and the principle behind the models in details. Like we mentioned before, there are two different approaches and the roots of the denoising diffusion probability models. We'll explore these two approaches, following mostly by these two blog posts. Start from this one. Let's start it by comparing the models that we have learned before. The game model is a little bit different than the others, but diffusion models, flow-based models, and the VAE, variational autoencoder, share some similarities. Let's recall the major difference between the variational autoencoder and the flow-based models is that for the variational autoencoders, we train the encoder and train a decoder together. But for the flow-based models, we only train the flow models. Because of the design of the model architecture, we can get the inverse model automatically. Although the flow model works like an encoder and the inverse model works like a decoder, they are essentially just one single model. It is that it is reversible, so we can use it in both directions. So for diffusion model, we kind of have a similar approach to have an encoder and decoder, only that the encoding is more like adding noise and the decoding is kind of denoise. So unlike the VAE and the flow-based model, the encoder part is not trainable. We already know what the encoder is because we already know how to add the noise into the image. So there's no training on this part. We only need to learn the decoder, which is the denoiser. So let's first discuss the forward diffusion process. Adding noise can be a very flexible and abstract process you can apply to many different situations. However, because the primary object we wish to generate is image, so let's discuss what exactly we do to add noise on an image. Let's first imagine an image as a vector. So for example, if an image has a resolution of 500 by 500 and 3 color channels, so we treat this image as a vector of length 500 times 500 times 3, which is equivalent to say that a vector of length of 750,000. So the vector has a dimension of 750,000. How do we actually add noise on it? We add a Gaussian noise on each of the component of these 750,000 components in this vector. However, because we usually do this for images and the terminology component and 750,000 dimensional vector can be a little intimidating for the people that's not familiar with linear algebra. So in what follows, I will use the term pixel instead of saying the component. So when I say let's say that we add an independent Gaussian noise to each pixel. Strictly speaking, this is not entirely true or accurate in our situation because each pixel contains 3 components, not just one. But pixel is more intuitively understandable. So let's just start by considering we are dealing with an image of grayscale. In a grayscale image, each pixel will only have 1 channel instead of 3. So each pixel is corresponded to a component. But by imagine we add noise to the image, to the pixel, we can imagine an image is getting noisier and noisier. It's easier for us to imagine the process of adding noise. So I'm just using this terminology. What if we are dealing with a color image, like with 3 channels or 4 channels? It's pretty much the same. It's just we are adding the noise independently, each channel of each pixel. So start with x0, which is the original image. We add some noise to each pixel independently, and then we get x1. Then we add another round of noise. We do the same. We add an independent Gaussian noise on each pixel, and we get x2, and then we get s3, x4, s5, and so on. If we do it long enough, say for the capital T steps, if the capital T is big enough, we are getting something very similar to a totally random image with pure Gaussian noises. So let's read the formula here. These formulas describe the exact process for adding noise that we just described. The process of adding a noise on xt-1 and it becomes xt is denoted by the probability distribution Q. So each xt-1 and xt is a vector. In our case, they are just an image with the same shape of the original x0. It is much noisier. When t getting bigger, the image is getting noisier. Suppose we already have our xt-1. Because we are adding a random noise, so the image generated in next step xt can be considered as a random distribution, depends on xt-1. And we are using Gaussian distribution to describe the conditional probability distribution because we are adding some noise. It is probably easier to see the formula here. So this formula might be easier to understand. So basically, this means the images at the step t-1, and epsilon here is the standard Gaussian noise. We are mixing up the image at step t-1. We are mixing up the image of step t-1 with a noise, and this mixing is a weighted mixing. So I'm giving a weight here. The image has a weight square root of t. You can imagine this number is a big one, like 0.9. And the weight of the noise is square root of 1 minus alpha t. You can imagine this weight as something smaller, like 0.1 or 0.2. We don't need to be worried too much about why this is a square here and why these two weight has some relation. The major reason we use this weight is in later steps we'll find this weight can simplify our calculation. But the idea is we are mixing up the original image with some noise. So obviously the weight of the noise control the scale of the noise that we add into the image. The reason that we need to have a weight for the original image or the image at step t-1 is because if this weight is less than 1 and we have a lot of it, eventually the effect of the original image can be guaranteed to turns to 0. The effect of the original image is going to be scaled down. So for a suitable weight, we are going to eliminate the effect from the original image, guarantee to eventually reach totally random. If you compute these two guys together, you can see that it is in fact a Gaussian distribution. Because the standard Gaussian distribution here has zero mean. So the mean of this guy is exactly the first term, because the second term has a zero mean. However, the first one is fixed, so the standard deviation follows the scale of this guy. Because the standard Gaussian distribution has a standard deviation 1, so we know this one is simply a Gaussian distribution with the first term as the mean, and the scale of the second term is the standard deviation. So that's why the original formula can be written this way, because we simply write that the image of the next step has a distribution that has a mean of this guy and has a standard deviation of this guy. Note we have a capital I here. Capital I is the identity matrix, which is a matrix that has only one on the diagonal. And otherwise, every component in this matrix is just zero. In general, a multidimensional Gaussian distribution may have correlation in different components. However, if the Gaussian distribution is independent, then the covariant matrix must be diagonal. The covariant matrix will be diagonal. So this one simply means we don't need to worry about the correlation between the noise added to each pixel. When we add noise to this pixel, we simply just add a Gaussian random variable on it and doesn't care about what we add to other pixels. They are all independent. And this formula simply states that if we want to find the distribution of the last image, that is x capital T, which is the last image right here, just right here, then we can consider the process of adding noise step by step. So we only need to consider the product of each step. This formula may look a little bit complicated or maybe even a little intimidating, but in fact it is trying to tell you our process is simple. The reason that we can do this multiplication, do this product, is because each step is independent. So at each step, we don't need to worry about what happened next, and we don't need to worry about the noise added by previous steps. We simply add the noise independent to previous steps and future steps. We don't need, so that in fact means simple. Because if we have to consider what we did in previous step, such like, okay, if we add too much noise at first step, we should add less noise at second step. Or maybe like, if in the last 10 steps, 5 of the steps are adding a lot of noise, and 2 of them are adding some noise below the average, and the last 3 adding some noise that is roughly the mean average, or then we should do something at the current step. So you can see that if we have to consider the previous steps, things are getting more complicated and more difficult. I think maybe you didn't even realize the schema or the process can be that complex. But because we know that there are simple processes, or we know that there are many possibilities of defining procedure to add noise, so we have to specify that, okay, this noise adding schema is nothing but the simplest one. So we have to write this down and this down to tell you that, and you can see that, and this guy, to tell you, okay, we are adding noise to the image and using the simplest way, exactly the simplest way. So all these formulas are pretty much tell you, okay, we are adding noise in that simple way. We are not considering those crazy complex procedures we are considered the most simple way, at least in some sense, because we are still adding some parameters right here. One question you may be raised here is that if our intention is to make this formula to be easy, to be the simplest one, why not just using the uniform distribution? Why do we have to use a normal distribution? Because normal distribution has a more complicated formula involving with the exponential and the square root and the pi and lots of scary things. Why not just using the uniform distribution instead? The reason is the normal distribution, or we call it the Gaussian distribution, has a very good property. It has a very useful property. That is, if we sum up two independent Gaussian random variables, then the sum of them is still a Gaussian random variable. This is not true for uniform random variable. For example, if we throw a dice, the number is uniform. It is a discrete uniform distribution. However, if we throw two dice and sum the number, then you can see that it is no longer a uniform distribution. We are more likely to get a 7 than a 2 or 12. Our forward process is essentially adding the noise for many rounds. So Gaussian random variables has a nicer property that we can use to simplify our calculation. And after all, if you add a lot of independent uniform random variables together and consider the mean of it, it will look very similar to a normal distribution. Let's summarize the forward diffusion process. We are adding the noise to the image step by step using a simplest way to add the noise, in the sense that we add the noise to each pixel independently at each step, but we left a freedom to decide the strength of the noise at each step. Each step we can have a different strength of noise, and we have a freedom to choose different number of steps. Now let's derive some properties from this basic equation. From a definition, we know how to compute the probability distribution of xt from xt minus 1. That is, we can write down the distribution of next step depends on this step. What if we want to compute the distribution of the next 2 steps or next 3 steps or next k steps? So we can do that. To simplify our calculation, let alpha t to be equal to 1 minus beta t, and let alpha t bar to be the product of the alpha I here. So as we mentioned before, xt is equal to this guy, and if we compute the next step, we simply substitute xt minus 1 into the formula of getting xt minus 1 from xt minus 2. Then we can get this formula. And if we do this for multiple steps until we reach x0, then we'll get this one. So this is why we want to define this notation, so that we can simplify the symbol. And here we use the property that the summation of two independent Gaussian random variable is still a Gaussian random variable. So because the mean is always 0, we only need to recalculate the standard deviation. And this one is the standard way to compute the standard deviation of the sum of two random Gaussian variables. So it turns out we can use this formula to calculate the conditional distribution of xt condition on x0 instead of condition on xt minus 1. And it is not surprising that it is still a normal distribution, because we know that the addition, the sum of 2, 3, or many independent Gaussian variables is still Gaussian. If you are not familiar with Gaussian random variables, this remarks gives you the formula of how we add two Gaussian variables together. And if you are curious about it and want to really understand it, one way to do that is to simply try to calculate the variance So suppose if you have two independent random variable x and y and try to derive the formula of the variance of x plus y. Suppose x and y are independent. Since the Gaussian distribution is determined by its standard deviation and its mean, if we can compute the variance, then we can compute the square root of the variance, which is equal to the standard deviation. So that's how we derive the formula of merging two Gaussian together. Now let's talk about the reverse diffusion process. In the forward diffusion process, we already know how to compute the conditional probability of xt given xt minus 1. On the reverse diffusion process, we need to compute the conditional probability the other way around. That is, want to compute the distribution of xt minus 1 given xt. It may be difficult. One way or another, we can derive the relation. However, before we go into the detail, we want to see a big picture. That is, how do we use the reverse process to get what we want, that is generating images. We're always talking about the images, but we are really talking about the distribution of the images. We'll consider our images are sampled from a distribution. This distribution may be generate some image by some natural process. Maybe we'll consider all the pictures taken by the smartphone or all the images that is ever exist in a movie, or maybe potential images that can be extracted from a movie. But anyway, we are imagine a random distribution. It's only that we don't know what it is, but we know there is we're modeling it random distribution. So this is a visualization of a random distribution. So this one is our target random distribution. If we do the analogy, each image that we are consider is a single point in this graph. So this point might be an image, this point might be an image, and this point might be an image, and all of them are on this distribution. So when we do the sampling, we simply pick a random point from this graph. One of the major differences is that this distribution is very low dimensional because each point of it is only 2 dimensions. So one dimension is here. One dimension is there. As we mentioned before, if we consider the image we are consider is very high dimension, some dimension like 750,000 dimensional vector. But here we are only consider a 2-dimensional vector. So each point represents a 2-dimensional vector. So when adding Gaussian noise, we are adding 2 independent Gaussian random variables here. 1-dimensional Gaussian random variables here. But they have the same distribution and they are independent. We add the Gaussian to each of the dimension. So it becomes spherical 2-dimensional Gaussian noise. So basically, each point is going to, when we add the noise, each point is going to move around for a small step. And after a lot of steps, it will add some noise at each dimension. And also because of the scale, the mean of every point is going to be closer and closer to the origin, because we are multiply a weight to less than 1, a weight less than 1 to the origin. So that was the forward process. And we'll get something very close to a truly random Gaussian distribution at this point. So you can see that it is more dense at the center and more sparse when the radius is bigger. So this one is the 2-dimensional Gaussian random distribution. So for the reverse process, first we generate a random sample from the Gaussian random variable. Although you can see the blue distribution right here is generated from the forward diffusion process, and this distribution is generated using like a random number generator to generate a Gaussian random variable. But because they are very similar, when we get the setting right, they are indistinguishable to each other. So we can apply the reverse process to this distribution. So each time we are only generate one point right here, because each image, or in this case, the image of noise is just a single point. But if we generate a lot of things, if we generate a lot of sample, it will look something like this one, and we can observe the distribution more clearly. So by using the reverse diffusion process, we can simulate the process, and it will get back to the original distribution. So the idea is that because we know that the distribution are at the final step, so we can simply generate a Gaussian random variable, and then we reverse the process. Then because we can get the initial distribution, and this one is, in our case, for images, we are showing some interesting images. So there's no issues to generate a random variable here, and there's no problem because we already have a reverse process, so we can do the reverse process. This is also doable, and if everything goes well, then we'll get some images that looks like real images. Okay, let me switch the theme to be a light theme, because some of the formula we're seeing here require a white background. So let's first look at this equation here. This is something that we can derive directly from the formula. That is, we can compute conditional probability of xt minus 1 given xt and x0. This is not the final things that we want to have. What we want is something like this one without given x0. So xt to compute xt minus 1 only depend on x. But for the first step, let's compute this guy. This can be easily derived by the Bayes formula. By using the Bayes rules to compute this one, we only need to compute the right hand side, and all of these terms are easily derived from the forward process, because this is just compute xt given x0, and this one is to compute the probability of xt minus 1 given x0. Already got that formula before, and this one also looks different, but in fact we don't need to consider this x0 because xt is directly depends on xt minus 1, no matter what x0 is, since we already know the xt minus 1, because xt minus 1 comes later, so we can simply ignore this x0. So this one is from a definition. Each of these terms is a normal distribution, and we know what the mean and the standard deviation of this normal distribution. However, it is difficult to compute the probability of xt minus 1 without given x0, because the whole process depends on x0. However, we cannot give this information because x0 is the target we wish to approximate. So it makes no sense if we give information of x0 to calculate our formula. This is the thing that we don't know and we want to know. So instead of derive the formula directly, we are using the machine learning to train a model to do the job. So let's go back to the above figure right here. So because this guy is unknown, we are going to try to train this guy instead. So although we don't have the exact formula of x0, but when we do the training and we are taking data from the training data, so in principle, it is possible to learn the information of x0, to learn the information of the distribution of x0 in the training process. So that's why we can use machine learning to compute the reverse process. Because this process looks similar to the variational autoencoder, we can use a similar technique to derive the loss that we can use to train the model. So let's go back to the formulas. So we are still aiming for log likelihood, but using the similar technique, we can have an upper bound of the loss function. Looks like this one. There's an alternative way to derive the formula by using the Jensen inequality. But anyway, we can use this formula, LVLB, instead of directly optimizing the cross entropy. And we can further expand this one into several different terms so that each term is more easy to be evaluated. So if we expand this guy by doing some calculation, and we can find that we can organize it into 3 different terms, which we call LT, LT minus 1, and L0. Although the computation is a bit toward the complicated side, but we are simply split the computation step by step. We simply split the computation for each step. So that's why this loss comes with a time step. All of these things are some Kerr divergence, to compute some Kerr divergence, and all of these guys are normal distribution. I haven't said it before, but we're modeling the PC so that the output is a normal distribution, just like what we do for the variational autoencoder. We can see that here xt is the total random distribution, and this one is the model we are trying to denoise from x1 to x0. And this guy is the denoise step from xt to xt minus 1. All of these Q things are from the forward process, so we already know the values of all of these guys. They are just normal distributions, and we can compute everything because we know how to compute the Kerr divergence of 2 normal distributions, given we already know the mean and the standard deviation. So in fact, if we further simplify the formula, eventually we'll get something like this one. So especially if we are focusing on the noise things, we'll get something like this one. So how to interpret this formula? The formula basically says that we are trying to predict the noise, or epsilon is a noise, and comparing it with the true noise, and we compute the mean square error. So although the computation is very complicated and very long, but the result we are getting is simply the mean square error between the predict noise and the actual noise. The only difference is that for each different step, we have a different weight. So by this formula, the loss of each step has a different weight, depends on the steps. However, on a paper that is, I think it's a DDPM paper, it further simplified the objective and ignore the weight totally and argue that it converges better. So if we remove this term, then it simply becomes the mean square error. So that's why you see the code. If you see the code of like stable diffusion or other diffusion, it looks like it simply compute the mean square error. Because originally the formula has a weight right here, but some study suggests that we use a uniform, we use a constant weight for all steps instead of using a way derived from formula. So that's how it becomes the loss right here. So if you just look at the code, it just looks like a simple mean square error loss. So it turns out for the training and the sampling, we are actually simply doing something like a denoise autoencoder. So despite the long and the theoretical way to derive the formula, it turns out in practice, the diffusion model works just like a step-by-step denoise autoencoder. The loss function is no different than a standard denoise autoencoder because it is simply a mean square error loss. The only difference, or maybe we should say the slight variation, is this denoise autoencoder works on different level of noise. So we're given a step here. We are given a step here in our model, and the model is going to do the denoise according to the corresponding level of noise, depends on this time step. And it doesn't do the denoise in one step. We are splitting the noise level into time steps. So the denoise autoencoder do the denoise step by step. So this is true in the training and in the sampling. Another approach is using the score matching or score model to derive the formulas of diffusion models. We are primarily following the broad path of Yang Song, but although it is a very good read, but the text is a bit longer, at least for a beginning. So I'm having a summarize right here so that we can quickly introduce the basic. So at the beginning, we are still doing the log likelihood modeling. So in particular, we model our probability like this one. So the reason that we do this kind of thing is, in fact, we are modeling our output, our neural network as f theta. But because this one is a probability density function, so it has to get non-negative values. In order to make the output of our model to be non-negative, we feed the model output into an exponential function so that we can guarantee that the output of exponential and the negative f theta x is always positive. Another requirement of a probability is it has to be summed up to 1, or if you considering the continuous distribution, the integrate of the density function should be equals to 1. So we have another constant here, z theta. It depends on the f theta, but it is a constant. It serves as a normalization constant, so we can make sure that p theta is satisfying the condition of being a probability distribution. This type of formulation is reasonable and very common. In fact, f theta is often called as an energy-based model. We can train it by maximizing the log likelihood, and because we have the exponential here, the log works nicely here. However, because we still cannot get rid of the z theta, to compute z theta is very, very difficult. It is actually intractable, just like what we discussed when we talk about the variational autoencoder, because we have to do integration all over the whole space. The space is too big. So one way to that is to approximate the normalizing constant like we do in variational autoencoder, or to restrict the model to be like autoregressive models or like normalizing flow models. So that's the two approaches to get rid of the z theta. For the score matching model, it uses a different approach. It gives up the goal to approximate p theta itself. Instead, we are trying to approximate a different target, and that is the score function. The score function is in fact the derivative, actually a gradient of the is a gradient of log px. We do not trying to approximate log px, or we are trying to approximate the gradient of log px. The basic idea is in the spirit of the fundamental theory of calculus. That is, if we know the derivative, then we know what the antiderivative is, and vice versa. So this one is the derivative, and if our plan is, if we understand what the derivative is, we should have enough knowledge of what the antiderivative is. The antiderivative is the log p. So there are two obvious questions we should answer. The first one is, does this score function actually any easier to compute than the original log? That's the first one. And the second one is, even if we compute this score function, can we actually use it to do the sampling so that we can generate image? So we are trying to answer these two issues. We start from the first one. Since that we take the gradient, and our gradient is respect to x, and there's no x on z theta. Z theta is a constant, so the gradient is 0. So we can get rid of this z theta and only need to compute this guy. So this is a good start, but we still need to calculate this one as our loss. It turns out we can train this model by using Fisher divergence. So the Fisher divergence is this guy. Looks kind of like a mean square error. However, this loss target has an issue remains, that because this is the real distribution, S theta is a score function and the px is a real distribution. We only got the training data set. All we know about the true distribution is the training data set, which is a sampling, which is supposed to be a sampling from the real distribution. So we only got a discrete sample of from the true distribution. But this one requires us to do the derivative. So we have no idea how to do this one. So this comes to the method called the score matching. Score matching is a method to compute this one, to get around with, to compute this loss without compute the gradient of log px directly. It uses some calculus tricks to do. Basically, it simply computes the same integrate, but using a few calculus tricks so that we can around the difficulty. So for the answer of the first question, we can compute the score function. At least, in principle, we can compute the score and use this loss to train a model to approximate the score function. So the answer to the first question is positive. So how about the second one? How do we use the score function to do the sampling and generate real images? The answer is that we can use the Venn dynamics to do the sampling. So let's go to the blog post because it has a nice animation. So Venn dynamics is an iterated method, so that if we know the score function, then we can approximate the Venn dynamics is an iterated procedure that allows us to draw sample from the distribution if we have already know the score function. Although it looks very magical, but the idea is quite simple. Because we already know the gradient. Gradient is like a direction, like an arrow, like a force field. So we can start from any point in a space. And in each iteration, we are moving our sample towards somewhere more likely to be drawn, because we know the gradient of the distribution itself. So we can move our And the gradient tells us so just like the gradient descent method, we are trying to use something like a gradient ascent method, so to maximize the probability by using a gradient information to maximize the probability. However, unlike the gradient descent method or gradient ascent method, we do not wish our sample to converge to the maxima value. We wish it to converge into a distribution like the original distribution. So it requires to adjust the turn a little bit so that we can make sure if we randomly draw something and following the iterative procedure, it will end up has the same distribution. So you can imagine that it is kind of like a gradient ascent algorithm with some random noise turn, so that it won't converge to a single point. It will have a probability, it will converge to a probability distribution. So this one is the formula for the Levene dynamics. So if you look at this term and this term, it looks like a gradient ascent method. Only that we have a z I here, which is a random term. So you can consider it as a randomized gradient ascent method. So here is the illustration of the procedure of the dynamics. However, the story is not finished. Although we already solved the two obvious problems, if you really do the implementation, you will still see that the result is not satisfying. So one, that's called the above method, the naive score-based generative modeling. It has some pitfalls that will prevent the result to be very good. One reason is that our samples tends to be sparse and actually accumulated in some point and very sparse on other place, like the graph is like the extraction right here. So in this case, if our score matching is pretty good, then if we have a perfectly accurate score function by using the score matching, then everything should be fine. However, because our sample is mostly centered on this and this part, it doesn't have any sample around other place. So the score matching function doesn't converge well or doesn't have a very accurate value around other areas. And as the Levene dynamic procedure works, at the very beginning point, we are sampling a sample randomly from the space, the whole space. So it is likely to be sampled in an inaccurate area. If it is sampling from an inaccurate area, then chances are it will remain on if we do the iterative procedure, it will remain on the inaccurate area because we don't have much sample on this area, so that we have no chance to train it to be more accurate. So you can see, although in the reality, the real score will have a correct gradients to lead the sample toward a more populated area, a more dense area, like these arrows. However, if we didn't train the score function accurate enough, if the sample, we draw some samples starting from here, it will likely to end up in the middle because the score function is not accurate. So although our method is theoretically sound and is quite efficient because we're using a score matching and the Levene dynamics, but because of the imbalance distribution of the data, because the data is central at certain point and sparse at the rest of the space, so we still cannot train the score function accurate enough, at least not with the naive method. So one way to do that is we simply perturb the data, because our main issue is that distribution only central in a few small spots. So if we do the perturb, something similar to the Gaussian blur on image processing, then we can make the support of the distribution getting wider and wider. In this case, we can train the score function accurate enough. But how large the noise should be? What is the magnitude sufficient? If we make the noise too large, because we only converge to the score function is only converge to the noise data. So the sample it generated is an image contains noise. That is not what we actually want. We want to generate some image has just like the real images. We don't want to generate images with noise. So how do we solve these issues? It turns out we can use multi-step to do so. So first, we are trying to train a model that with very noisy data. So we get a very large magnitude of noise so that it can converge easily. Then we reduce the noise a little bit and train another model. And then we reduce the noise even more and train a model that has less and less noise. So after we have a model for different scales, then we can do the sampling. Start from the most noisy models. And we do the Venn dynamic iterative procedure on the most noisy models a while, so that the point is close to the more populated region enough. Then we use a model to have a smaller noise, and we run the sampling procedure again. So the sample is supposed to more close to, so we start from the rightmost picture that with the most noise. And after a while, where the sampling is supposed to go near the denser area. And then we use a trained model with this noise and make the sample, do the iterative procedure to make the sample to even closer to the dense areas. Then we run a model that is trained with minimal noise. Then we can get the sampling procedure to converge. And also at the final step, it will converge to the right distribution without noise. So if you are already doing the procedure that described above, you will see the images look like this one from the right to the left. This looks extremely similar to the denoise diffusion models that we described earlier. So although we are starting from a different approach, a totally different beginning, it turns out we are getting very similar formulations. Not only the result look similar, but you can see the actual formula is going to be quite similar. Both approach has its own advantage. So in the score-based explanation, in the score-based approach, we can see why the noise part is necessary, because it is used for solving the issues for the uneven distribution of the data, of the true distribution. And because of the uneven distribution, it causes the inaccurate score function. So we use the noise to solve this issue. So here are some nice animation to show how the score matching models work. The other advantage of the score-based model is it has some relation with the stochastic differential equations. Just like when we introduce the flow models, it is very natural to connect the normalizing flow with a differential equation. So the score-based generative model is also has a very strong connection with the stochastic differential equation. We can model the whole score-based thing with in the language of a stochastic differential equation, and using the tools from solving differential equation to solve them to help us to find the score function. And here are some notebooks that implement this result. And moreover, we can have a more fundamental understanding of how these models works. Okay, so today we'll cover some fundamental principles and the theories about the diffusion models. The first one is from the denoising procedure, and the second one is from the score-based models. Just like when we introduce the transformers, when we try to understand how these models work, the best practice is to implement one by ourselves. Perhaps for the low dimension one, like the toy examples in like 2-dimensional, to test if you really understand the stuff. However, there are more to the denoise diffusion models other than the fundamental principle or theorem that we discussed today. For example, we haven't covered how we use text to generate images, because you can see that there's no text or prompt involved in these principles. So how do we actually use the prompts or text to guide the models to generate the image that is related to the prompts? These are the other stuffs we are going to cover next week.